Back to your notes online for AP Stats. Going to continue talking about normal curves, normal distributions. And last night we talked a little bit about how to use the empirical rule, the 68, 95, 99.7 rule, to help us find proportion of individuals or proportion of observations in certain intervals under that curve. And they all corresponded to standard deviations, right? So if we wanted to know, so we go back to this ACT distribution, and we wanted to know, sorry, some technical difficulties here with my board. If we wanted to start finding proportion of observations that are somewhere, that fall on scores somewhere around standard deviations, not around, but on them, right? Then we can use that empirical rule to help us find those proportions. We broke up the normal curve into different pieces and talked about what proportion of individuals are in those specific intervals, and then we can just add those together to get whatever we need. The question today becomes, all right, what if I want to know what proportion of all test takers scored below a 21? Well, 21 is actually going to fall somewhere right in here, right? Which is not at a standard deviation. We don't have any idea what proportion of individuals, what proportion of test takers scored in this area right here. It's not 68% anymore because we're not in between the first two the first standard deviation. So what do? If I want to know what proportion of test takers scored less than a 21, we could use the empirical rule to estimate this, right? So if in the middle here is 68%, like the empirical rule says, that means 32% are outside of that, and strictly less than the first standard deviation, there would be 16%, right? So there's at least 16% in here, okay? Well, since 21 is basically 2/3 of the way down this standard deviation, right? From 23 to 20, we can almost break this interval up into thirds, 22, 21, and then get to 20. So this would be thirds. Well, we do know that because of symmetry and because of the middle proportion being 68%, that this area is 34%, right? So I could take this 16%, and then I'm going to have to add this sliver to it to get to 21. Well, how much is that sliver? Well, since we can consider this as cutting this interval up into a third, then I just take a third of 34, right? So I take 34% and divide it by 3. So it'd be 16% plus, what is that, 11.3% repeating, which we would get 27.3%, okay? So that's a way to estimate it. But look at the curve and look at what I was talking to you about. I'm talking to you about taking this interval and cutting it up into a third. Is this sliver really a third of this entire area? Well, since this guy is a curve and this curve falls down, hopefully you're sitting there saying, well, no, not exactly, right? If this were a rectangle, then fine. This would be a third and we'd have no issues whatsoever. But it's not going to be quite a third. Now, that's why this is an estimate and it's not going to be exactly right on. But that's the idea behind using the empirical rule to estimate. Now, we could do this for score above 30 and then go through all of this, but I don't want to. I don't want to use this to estimate. That's about as much as I want to do with estimating this stuff. So instead, let's go back and talk about, before we go back and talk about what we mentioned at the end of class, let's talk about how you would get to an exact area, right? Remember, I'm really wanting to find this area right here. How do I find that exact area? And I was corrected at some point yesterday. It's not a derivation. It would be an integration, right, under this curve. I have to take the formula for this curve and integrate it with the bounds that would correspond to this interval. And again, If I wanted to do calculus, I'd go teach calculus, and I don't want to do that. So I don't want to do calculus. So in statistics world, there's got to be a better way. And it so happens that there is. And this is what someone has graciously done for us. And so we go back to what we talked about at the end of class, right? If I take any normal distribution, it doesn't matter what the mean is, and it doesn't matter what the standard deviation is, if I convert all of those observations into z-scores, and we talked about this even before today in class, what happens to the distribution? Well, remember that a z-score calculation is nothing more than transforming your data. And so shape stays the same. So if I take this distribution, which is that heights of young women that was in the Check Your Understanding from last night, and I convert all of those heights, all of those young women's heights to z-scores, then my shape would stay the same. It started off as normal, so the new shape is going to be normal. Not a new shape, it's the same shape. What happens to my center? And we did this a few days ago. The center for this distribution, if I convert them all to z-scores, would just be 0. And the standard deviation would just be 1. Okay? If we need to review this, let me know tomorrow in class and we'll talk about that. But it doesn't matter what the mean standard deviation is. If I took this distribution, which you have no idea what it's for, and it makes sense because I just made it up, but it's a normal distribution, and if I converted all the observations to all these values to z-scores, it would still be normal, the mean would still be 0, and the standard deviation would still be 1. Same thing for this distribution. And I could go on forever and ever and ever. Every normal distribution, it doesn't matter what the mean or the standard deviation is, if I convert those values to z-scores, then my new curve would be normal still, with a mean of 0 and a standard deviation of 1. This is in z-scores. When we talk about z-scores, we're talking about standardized scores. So we're standardizing all of our values for our variable. Okay? Well, then it stands to make sense that this curve right here, whose mean is 0 and standard deviation is 1, and it's a normal curve, is called the standard normal curve. Okay? Or a standard normal distribution. Okay? Why is that helpful? Well, because instead of taking this curve, well, we'll go back to this. Instead of taking this curve and integrating under this curve to find this area, since this value that we're looking for does not fall in standard deviation, and then having to do the same thing for this curve if we're not on standard deviation, then I have to go integrate this curve, and then I have to go integrate this curve, and because all of the mean standard deviations are different, the formulas for these curves would be a little bit different, then it would be a lot of integration to have to do. But this idea of standardizing all of these values means that I can take any normal distribution and tie it to a single curve that would have the same proportion of individuals in these intervals, right? Remember, position doesn't change. So if I were to do some integration and realize that 26% of the individuals fall less than this value, then when I standardize, position doesn't change. So 26% of the individuals would fall below this value, whatever this was, whatever z-score this was. Okay? So we're standardizing all of our values down into the same curve, right? And why is that important to us? Because now, instead of integrating 3 or 4 or an infinite number of times, because we have different means and standard deviations for different distributions, all we have to do is integrate once. And when we integrate once, it will take care of any other normal distribution out there. All we have to do is convert back and forth between actual values and z-scores. And we've talked about how to do that already, right? Luckily for us, someone has done all of that integration for the standard normal curve already. And all of that integration has been lumped into one gigantic table called Table A. And this is in the back of your book. Table A is in the back of your book. It's also in your blue formula packet. You'll have access to this table on the AP exam. And what you're looking at here is in a collection of z-scores. So when we take our values in our distribution and convert them to z-scores, then we can use those z-scores in our integration to find proportions of individuals that fall in certain intervals. And someone has done all that integration for us and has put all of those proportions right here in a table. Between this page, which has all of your positive z-scores in it, and the page before it, which has all of your negative z-scores in it, all the way out to 3.4, negative 3.4, and out to positive 3.4, which means what? Just about 3.5 standard deviations either above or below the mean. Okay? So this table of proportions represents any possible interval that you might want to find the proportion of individuals in for any normal distribution. All we have to do is convert them over to z-scores. Okay? So one curve, one location, one set of numbers, not too hard to do. Again, we don't want to integrate, so someone has done it graciously for us and put all the values in a table. Okay? And so now we can use this table to help us figure out these proportions that we were trying to find before. And here's how we're going to do that. Okay? First, for 21, and let's see, we'll scroll down here because there's another space here that has us use the standard normal table. And so that's what this says, right? If your distribution is normally distributed with a mean of mu, a standard deviation of sigma, and we have a particular value that is the number of standard deviations, so then we can take that value and convert it over to a z-score, which again, z-scores tell us the number of standard deviations away from the mean. Okay? Like we just said, the standard normal distribution has a mean of 0 and a standard deviation of 1. And when we convert our z-scores, there's our reminder of our calculation, right? It's the actual value minus the mean divided by the standard deviation. So now let's a little bit more accurately answer or find these proportions that we're going to do at the top. First, for a score below 21. Like we were saying, so this is 23, this is 26. Again, this is this ACT distribution. So 21 falls right here, not on a standard deviation. Okay? I still want to know what proportion of individuals are less than 21 that scored below, what proportion of test takers, need to add context. What proportion of test takers scored below a 21? Well, to do that, I'm not going to integrate this curve. I'm going to convert down to z-scores and go use the table that someone has done integration for us in. So how do we do that? Well, I need a z-score first. I got to know where 21 is in this distribution. How many standard deviations below the mean? And it's going to be below because it's less than 23. Right? So we go 21 minus 23 and then divide it by the standard deviation of 3. Well, as you might expect, it's negative 2/3, which is negative 0.67. Round to the nearest hundredth, and I'll show you why to the nearest hundredth in just a second. Okay? Which makes sense because we talked about this sliver maybe being a third of this curve. That's because 21 is a third. 1 is a third of 3, and anyway, we broke this thing up into thirds, and 21 is 2/3 of the way away from the mean. So negative 2/3, negative 0.67 when you divide that out. Okay. Now, I want the area under 21 to the left, right? And that's important because now what we need to do is go in our table and find this z-score, negative 0.67. So we pull up our table values and we go looking for negative 0.67. Well, first and foremost, this is the positive side. So my negative 0.67 is going to be in here. Oh, I got to pull this out. This is going to be kind of hard to see the numbers at first, but I need to show you how the table is laid out. Right? So the left-hand side here lists z-scores, and the numbers that are used here are decimals, right? So we're going to at least report our z-scores as some decimals. And you can see here that it shows the ones digit, the tenths digit. And then if you look across the top, it carries out the decimals to the hundredths position. All right, so that's why we want to round all of our z-scores to hundredths, so that we can put together this column and this row into our z-score. So we're looking for negative 0.67, right? So we're down here at negative 0.6, and then we need to run all the way over to where the sevens, the hundredths position is a 7, and that gets us to this guy right here, okay? This 25, or 0.2514, okay? Now, what does that 0.2514 mean? Well, it corresponds to the proportion of individuals, right? And because of the way this table is laid out, it's the proportion of individuals that's less than negative 0.67. And how do you know that it's less than? There's a picture right above the table that's going to remind you. Table A is always going to give you proportions that are less than a particular z-score. We have to use the values in this table in such a way that it will give us the different intervals and the different areas that we want. Right now, we want to know the percent of test takers that scored less than a 21 and strictly less than. So that means I can take the table value and make that my proportion. So how many, what proportion of test takers scored less than a 21? Well, since 0.215 was that percentage in that table, then the symbols, we'll talk more about symbols when we get to probability. For right now, P can stand for proportion. Proportion of individuals, proportion of test takers that scored less than a 21 would be, that's not good. I'm trying to write with the mouse. Would be 0.2512, I think it was. 14, yeah, 14. And so about 25%, okay? Now, compare that to what we did up here when we were trying to estimate. We were trying to estimate it, we got 27.3%. So while 27.3% is close, it's not very different than 25%, but this 25% is a lot more accurate, okay? We can get even more accurate than that, but we'll talk about that in another evening, okay? So we can carry this on. What proportion scored above a 30? Well, we do the same process, right? So z-score, we got to find out where 30 is in the standard normal curve. How many standard deviations away from the mean is 30? So we take 30, subtract 23, divide by 3. We get 7/3, which corresponds to basically 2.3. Okay? Above 30. So I sketched this area out for the first one, and I want to do it for the second one. And you're going to do it every time you use the standard normal curve. You need to sketch out your area. So this is 29. You can't. This got cut off, but out here is going to be 32. So I'm talking about this area right here, and here's why. And I'm going to show you why you need to shade the curve every time. Okay, so we know that 32 converts down to a z-score of 2.3. So we go to our table, and we go look for 2.3. It's positive, so I need to be on the next page. I got to go find 2.3. Actually, it's 2.33. I just didn't do what I told you guys to do, and that was carry out to the nearest hundredth. So I got to go 2.3 and then carry this out to 2.33, which is all the way out here. Okay? Now, if you have shaded your curve the way you're supposed to, then when you see 2.33 and you get a value of 0.9901, then you're going to come back to your curve, you're going to come back to your problem and say, okay, that means that my pen's dead again. That's what that means. Hang in there for a second. Let's see. There we go. Then that means that what? This is 99.01%. So apparently, 99.01% of test takers scored above a 30. Look at the area we just shaded. Is that 99% of that curve? No. So what in the world happened? Well, remember that the book gives you area less than. Area less than, right? We want area bigger than, above 30, right? Above 30. So what do? Well, we have to remember that this is a density curve, and that the total area under a density curve is 1, or 100%. So we got to take our value and subtract it from 1. And when we do that, we get 0.0099. Okay? Which means that roughly 1%, right, because this would be 0.99%, roughly 1% of all test takers scored higher than a 30 on the ACT. Okay? So you got to be careful. The table always gives you proportions that are less than a particular z-score. So if we want more than, we've got to subtract from 1. Okay? Now, this could actually help us. We can actually work backwards from this as well, right? I'm trying to pull this out. So this last question, what score would you need to get in order to score in the top 5%, right? In the top 5%. Now this is a little bit different. We don't have a value yet, right? All I know is that the area under this curve needs to be 5%, and it needs to be the top 5%, right? Well, we need to work our way back to a score. We need to know what score you'd have to get to be in the top 5%. Well, since we're working in this standard, so what we can do is we can get to the standard normal curve, find what z-score corresponds to 5% of the z-scores being bigger than it, and then take that z-score and work our way backwards into the actual score, right? Convert back to our test taker distribution. So how do we do that? Well, again, the table in your book gives you proportion of individuals that are lower than a particular value. So if we want 5% to be higher than this value, this x, then we want 95% to be lower. So I need to go find 95% in the table. Okay, so we go to the table and we start looking for 95%. Now remember that along the margins here are your z-scores. It's in the body of the table that give you proportions. So where's 95% in this thing? Well, you look and we find that we land right here. Here's 0.9495 and 0.9505. Okay? Neither one of them is exactly 0.95, so what do we do? Well, if you're ever between two values, then you want to round basically and find out which one's closer and use that one. Now this one, we're right smack dab in the middle of. So we could take these two z-scores and average them, right? So this corresponds to 1.64 right here and 1.65 right here. If you average those two, you get 1.645. So we could use that as our z-score, 1.645. So the z-score that corresponds to the top 5, to a score you have to get to be in the top 5% is 2.645. That's your z-score. How do we turn that into an actual test score? Well, we convert back. We use our z-score calculation. So our z is 2.645. We don't know what our, all right, so some technical difficulties again, sorry. As I was working that out, I was corrected here. It's actually not 2.645. It's 1.645. Anyway, we're still back in our z-score calculation. So I need x minus the mean, which is 23, standard deviation, which is 3. And we go solve this equation, right? Put this over 1, we cross multiply, and we get x minus 23 is equal to 3 times 1.645, which is 4.935. And then we simply add 23. And so we get 27.935. So you would need to score basically a 28. Since you can't score a 27.935, you need to score about a 28 to be in the top 5%. And so that's how that works. Okay? That's how the table works. Okay, so that's basically all there is to it. Now, there's a lot of different ways we can use the table. We haven't even talked about how to use the table to find intervals, not just less than or more than, but if we want to be between two values in the standard normal table. But that's in your check your understanding for page 119. We'll see how good you guys are at thinking through that. So try that, check your understanding on page 119. And outside of that, using the standard normal table just becomes a matter of doing a bunch of calculations with it, which we will definitely do. So that's it for the notes. You do have some homework in your text. If you want to get started on that, if you want to wait until we get to class so we can talk about this a little bit more, that's fine too. All right, have a good night. See you tomorrow.